Hi, in this video I'm going to show how to use encoding and embeddings for deep learning networks for natural language processing in Keras. Natural language processing has many applications. One of the most common is understanding text to match a search in a search engine or doing a translation between languages. And the deep learning networks do not understand text, they understand numerical tensors. So we have to do a conversion from text to numerical tensors. That's the encoding part. We're going to show different options in here. In addition, there's the embeddings. Embeddings is basically doing an additional encoding of those numbers into vectors, which convey semantical information of words and relationship within words. And I'm basically covering the first part of chapter 6 of the Deep Learning with Python book, which is in the references of this video. And I'm using the Keras library, which is a Python library based on TensorFlow. And for this example, I'm using Jupyter Notebook, which I obtained from the WinPython a package, which is very easy to install and free of cost. Okay, so let's get started. One of the basic ways of encoding is use a one hot encoding. In one hot encoding, we have a number for each word and then represent that number as a vector of booleans in which the corresponding index of the word is 1 and the rest of the indexes are 0. For example, in here we have two sentences we're going to iterate through each one of the sentences, and then use split command to go through each word and create a map between the word and the corresponding index, which is going to be the order in which they appear. So that's why we're using the length. Okay, so we get a dictionary like array, and then we're going to create the tensor that represents the one hot encoding, which is going to be the number of samples, the first dimension. Second dimension is the number of words, which is going to be 10. Notice that each sentence can have different number of words, so we're going to have a maximum number of words. So in this case, both sentences are below the maximum, so we're going to have some padding, and you can see in here that the final 4 words are 0 and final 5 words in here are 0. This is the padding. But for the example that we're going to do in here, which is reviews, movie reviews, the movie reviews have could have more words than the maximum that we're going to choose. So in that case, they are cut at some point. You're going to see that in a moment. Okay. Anyway, you go iterate through the samples and use the enumerate command that is going to assign a numerical value for each iteration. It's going to create an induction variable for the iteration. In the case of samples, there are 2, so it goes 1, 2, and this one is going to go 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, etc. This here is basically to make this work. So it's basically going through all the words, and then it's gonna go use the dictionary that we created to get the corresponding index, and that index is gonna be used to set the 1. The rest are 0. Okay, so you can see in here, you know that the D word is repeated, so it's gonna be 1 in both. So you can see that reflected in here. This is 1, the, and the again. Okay, so this doesn't look very memory friendly, and we're gonna see other options that are better. So we're gonna have a tensor here of size 220, and there's another option. We can do the encoding based on characters instead of words. So we're gonna do the same example. We're gonna use the string library to get the alphabet, which we're gonna have like 100 letters, and we're gonna create a dictionary from character to letter. I copy paste this from the book and it didn't work, so I had to do some changes to make it work. One of them is put the characters instead of the numbers as the key, the first value. So this zip command is gonna interleave the characters and the digit. So you're gonna have A is 1, B is 2, C is 3, etc. And then create a dictionary out of it. And we can see that we have 100 characters, and we have a map in which we go from the character to the corresponding encoded digit. Okay, so now let's create the one hot encoding for that, and we're gonna do the same. We're gonna create a tensor, and this time this is, instead of being this the maximum number of words, it's gonna be the number of characters in the alphabet. And again, I had to change this from keys to values because it didn't work. So okay, so it goes through all the characters, all the samples, and get the character, the index from the character, and put it into a tensor. And now you're gonna get a much larger tensor. So this tensor is 50 times larger than this one, and you might think that maybe this character encoding is more memory consuming, but that's not necessarily the case. It's gonna be like 5 times more in the number of dimensions in the second dimension, which is for example, if you have a review, a movie review with 100 words, then it might be 500. But the number of words in the older reviews could go to 10,000. But this is the number of words. The maximum number of words we could be 10,000. But for the alphabet, this one stays the same. So this doesn't grow because the alphabet doesn't change no matter how many words there are. So that's debatable if this has more memory or not. But still, encoding words is more convenient because human beings, we understand words. If you try to say a novel letter by letter, people are not going to understand you. So the same is for the machine. Is the words convey more meaning, so it's more convenient to encode words than characters. Okay, so let's run it. We can see I just grab a little bit because this tensor is much larger. But you can see that this is going to be the first character, and we have the one in here, second character, we get the one somewhere around here, etc. Okay. Now we're going to use Keras provide a library to facilitate what we did. Basically provide you a dictionary and encoding you the words. So that's the tokenizer. So the tokenizer, you pass these samples, and you're gonna feed the tokenizer to these words. So it's gonna figure out there's 10 words, and it gets you the samples, and the samples are gonna be encoded, and you can see the coding here. And you remember that the first word's the, which is the same, so you get 1 and 1 in here. But unlike what we did, this is case insensitive, so you're gonna see that this one is the same as this one. So you're gonna see 1, 1, 1 in here. What we did, it was a different number in here. Okay, so also it's gonna give you a dictionary through word index when you use this attribute or method, and you can see that we have almost the same, but case insensitive. And also when you use text to matrix, you get the one hot encoding. But the one hot encoding is a little different because we have for each word in the sentence we have a different vector, but he is adding them all together. Imagine that you're adding all of these, but if we have the same word twice in here, we're gonna see it. But if you put them together into one vector just by adding all these rows, then if you get a word multiple times, you're not gonna see it. But that's what this encoder is doing. Let me show here. When you get the one hot call result, you can see here. You get multiple. You only get 2 rows, and the rows is for first sentence, second sentence, and yeah. Okay. Okay, so let's keep going. Okay, also he uses a hashing trick that instead of using the index of the dictionary, it's basically doing the same thing, but instead of using the index of the dictionary, it's taking a hash out of the word and put it in here to do the one hot encoding. The problem with this is that if you have 2 words that happen to have the same hash, then some meaning can be lost. Some confusion can be caused in the neural network. Okay, so let's keep going. Now let's do the embedding. The embeddings are like encoding on top of the coding that we already did, but conveying some meaning of the word. For example, let's say that we have a three-dimensional embedding vector, and two for an embedding, if two words are close, is they're supposed to mean have similar meanings. For example, if instead of doing natural language processing, you are doing a processing of source code, then and for, which is a keyword in the C language, the embedding of that word, of that keyword, should be close of a while loop, of a while, which is also represents an iteration loop. So it should basically convey a meaning. And translations, if you go in one direction of that vector space, that translation direction has a meaning itself. For example, in here we're going in this direction from this word, and then a man gets converted into a woman, and a king into a queen. And another direction, it could represent basically the changing of the tense of the verb, or it could also represent going from country to capital. So in here, the embedding has three dimensions, but in reality, it could have many more dimensions to represent more features. And that is done in Keras through, okay, let me show you another picture. Also, the book showed this picture that comparing one hot encoding, which are sparse, high dimensional, to war embeddings, which are dense, lower dimensional. Okay, so we're gonna use this one. Okay, so for embedding, Keras has this embedding layer. The embedding, this is the sample dimension, and this is gonna be the output dimension, the number of features. In this case, it will be a 64 vector, but we're not gonna use that. Okay, so to try this example, we're gonna use the IMDb database. You might be familiar with it, but in case you don't, it's basically a website that has a huge database of a bunch of maybe most movies, and they have reviews on them. And what we're gonna do is take the reviews. You can see the reviews in here. Okay, so you can see that a review has a bunch of text, and we're gonna basically what the Keras already have a data set with this IMDb that has the text and the corresponding evaluation if it's negative or positive. So we're gonna train a neural network to be able to get a review in text and say if the review is negative or positive. Okay, so Keras already has that, so we're gonna preload that data set using the data. So we have the data ready to be fed into the neural network. We don't have to do any pre-processing. Okay, so let's see the shape of. Okay, so each of these, the X is gonna be the text, the actual review. So let's see how it looks. It is encoded already. Each number represents a word. So let's see the size of it. The size, it depends on the review. Each review is gonna have a different size. So, but that's a problem for the network. We have to clamp it, and we're gonna choose the number of 20. So we're not gonna allow more than 20 words. So we're gonna use the path sequencing, path sequences function. This is if the amount of words is below 20, it's gonna add 0 or something else, and if it is above 20, it's gonna cut it. Okay, so okay, and the y in here is gonna be the evaluation. So that's always gonna be 1. Actually, it's not gonna do anything because it's a scalar, so that length method doesn't apply. Yeah, so it's a evaluation. So some of them are that one is negative, this one is a positive review. Okay, so let's code it. Let me try this again just to get the length. 550. Let's apply these path sequences, and now let's run it again. Now it's 20. You can see it was cut. Okay, now let's get the shape, and now you can see the shape of the tensor is 25,000 samples, each one of them with 20 words. Okay, now let's train the neural network to train the embedding layer. Okay, so the embedding layer is gonna have a vector size, so it's like 8 elements in the vector, and the input is gonna be the 20 words. So let's create this and see the summary of the network. It's gonna use root mean square propagation for training the network, binary cross entropy to compute the loss, accuracy as the metric, sigma is a so yeah, so you have the embedding layer that is going to give you the semantic representation of each word, and then it's going to flatten it to be able to fit into a fully connected dense layer, which is going to do the most of the training, and the output is going to be a single element, which is a classification indicating if the review is negative or positive, and you can see it in here. This is basically the multiplication of these two dimensions, and the input is the words and the output is the embedding size. Okay, so now so if you take the first layer and we get its weights, let's run it. We can see that the size of the weights is the number of samples, and the output of the embedding vector, that's the shape of the weights, and we're going to use that later to be able to load some predetermined embeddings. We're going to do that example later. Okay, so let's train it with the training data from the IMDb dataset. Let's go for it. Okay, but now the accuracy is pretty good. Okay, so now we're gonna try it. We're gonna try it with raw data from the IMDb dataset. And for that, go to this website, download the zip file, and it's gonna have for some reason it's supposed to have a train folder, but it only had a test folder. So to make this example work, I'm using the test folder. Okay, another thing, I'm using Windows. I don't know if that has to do, but I have to put an R in front of this path to make it work. Also, when opening the file, I have to put this encoding. So watch out whenever you open a file, use Unicode encoding. Otherwise, it doesn't work. At least in Windows, it didn't work. Okay, so what it's gonna do is go through the negative and positive evaluations, and it's gonna use the directory as the label for the training. So this same label is gonna be using here to fill up the zeros and ones. And then for each file, if it is a text file, last 4 digits, then it's gonna open it and just read all into a text unit. That's when you read it into an element of their text array, that's gonna be the evaluation. Okay, so we're gonna see the actual review. So we have 17,000 plus samples. Again, each review has a different number of words. Let's take review number 100. There's a lot of them, so we can take the 1000. Okay, it's hard to tell which movie is this, but we saw in here that the reviews were a little bit longer. Yeah, probably some of them are short. Yeah. Okay. Anyway, so yeah, so if we take the same, we can see if this evaluation was negative or not. It was had a negative review according to the training data, the raw training data. Okay, okay. So if we sum all the positive reviews, positive reviews are 1 and negative are 0. So if we sum the labels and then take the length of the label, we can get number of positive reviews is 27%. It has some negative bias in there, but anyway. Okay, now again, let's use the tokenizer. In order to train the network with this raw IMDb data, we're going to use the tokenizer. We're going to provide the data that we loaded in here, the text. We're going to provide it to the tokenizer in here. And from that, we're using the same commands we used before, fit on text and let's text to sequence. We're going to get the encoded sequence for each of the reviews. Okay, so let's run it. Okay, so yeah, so we have a total of the same samples. It's the same thing, and yeah, so yeah, if we're gonna see basically the encoded sequence in here. Instead of getting words like we did here, we're gonna get numbers. Okay. Okay, now we're gonna also get the dictionary from the tokenizer as we did before, but unlike last time, we this time have 72,000 words, and that basically goes from the word into a corresponding a numerical identifier. Okay, now we're gonna pre-process the IMDb raw data into the arrays that we're gonna use to train the neural network. Okay, first we're gonna pad the sequences using pad sequences. Again, we're gonna limit the number of words to max length, and max length is, okay, let me find out. It's supposed to be 100. Whoops. Yeah, 100 words. And also we're gonna convert the outputs into an array. And then after that, we're gonna create a range of values for the first dimension, which is the first dimension is the sample, 17,000 samples. And then we shuffle those indices and then apply it again to the list in order to basically move them around to have some random order. And then we're gonna take the first for training samples. We're gonna use 2,000 training samples. Well, that's what I used last time. I'm gonna use a little bit more. Let me run this again. Okay, yeah, it's the same number, but anyway, I'm gonna use 20,000 training samples and 10,000 for validation. Okay, so the first 20,000 are from 1 to 20,000 are for training, and then from 20,000 to the end for maybe 30,000 is for validation. Okay, this is the shape of the input, which is the maximum number of words and number of evaluations. This negative or positive feedback. Okay, so let's keep going. Okay, for the embedding, we're gonna use a predetermined embedding. We're gonna load it directly into the weights of the embedding layer, and we're gonna get it from this website. And if you go to this website, you can download this file. Again, you put the R in front, use encoding, and once you load it, you have to basically the file has a bunch of lines. Each line in the first token that you see in the line is going to be the word, and then a bunch of numbers, and those numbers represent the embedding vector. So we're going to read it line by line. The first token, after splitting it into tokens, the first one is the word, and from 1 to the end are the embedding. And then we're gonna get an array of about 400,000 embeddings. There's a bunch of them. Okay, sorry, we have to run this and then this. Okay, so the embeddings that we have, if we, let's say the word bear, we have an embedding of size. It's gonna take a while. I'm gonna pause it. No, it finished, sorry. Okay, so if you take the var, you got that embedding vector of 100 elements. You can verify it in here. Yeah, 100 elements, all of them are the same size. Or you can use another word, a different vector. Okay. Okay, so now, but the problem is that this embedding vector goes from word to 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 embedding. But in the deep learning network, we're going from number to embedding. So we have to do some pre-processing into this array as well. And for that, we're going to use the dictionary that we obtained from the tokenizer. In here, we got the word index from the tokenizer, and that's the one that we're going to use to convert this embedding vector into to go from number to embedding vector. Okay, so let's keep going. Whoops. Okay. Okay, takes a while. Okay, we're using maximum number of 14,000. So yeah, we're gonna do the conversion. We're gonna create an array which is gonna be the size of the maximum number of words, which is 10,000. We're going from encoded word into embedding size, which is 100, and that's gonna be an embedding matrix. And then we're gonna iterate through the dictionary, which has the word and the corresponding numeric identifier. And if you are below the limit, then you're gonna get the embedding of the word using the embedding index that we got from Stanford, and then put that vector into a corresponding index. So now we have the embedding matrix. Okay, and the shape is 100, size of embedding vector, number of words. Okay, that's the number of the size of the dictionary. That doesn't have to. Okay, so anyway, let's go to create the network. Again, we're gonna create the layer, embedding layer. The max length is the maximum number of words, which should be 100. 100 words, that's the input, and the output is the embedded dimension size, which is 8. Let me just make sure about that. No, it should be 100 because yeah, that's the size of the embedding vector. So the output of the embedding layer is going to be embedding vector, and the input are going to be the encoded words, the words converted into numbers. Okay, so that's why we see 100 input, 100 output. Then when you flatten, you multiply the dimensions, and then we add an additional layer, an additional fully connected layer with 32 features, and again the final layer with the classification of negative, positive review. Okay, so that's your network. So we already pre-processed the training data in here that came raw from the IMDb database. So we're gonna use to train the neural network. Okay. Okay. So now let's put the pre-trained embeddings into the network. Let's get the weights. You can see that the embedding matrix has the same shape as the first layer weights. And so we just can assign the embedded matrix that we created here that we got from Stanford. We're going to assign it directly into the weights. And then we want to mark this layer as not trainable. We don't want to change the weights. Okay, so now we can train the neural network using the same methods, root mean square propagation, and using the training data from the IMDb database. And it should be fast because we are not training the first layer, we're only training the last two dense layers. Well, it takes a while, but anyway, when it finishes, we're gonna plot the results using these commands. I'm not gonna go in detail through them. It's basically taking the output, the history. From the history you get the accuracy numbers, validation accuracy, loss, and then just use the plot tools to show the results. Okay, so finish. Well, 93% accuracy. That's amazing. Let's see what happens. That's the training. Okay, something happened here. Let me run again. Okay, probably I might need to run it again. I'm gonna pause it to see if I can fix it. Okay, I got it to work. The problem was that I increased too much the number of training samples to 20,000. I reduced it to 2,000 again, and when training it, it gave me a lower variation percentage to 70%. I had it in 98 something because you can see the difference it makes. 20,000 from 2,000, it can go from 70 to 90%. But for some reason the something broke. Uh, okay, so in here you say that with small amount of data, it looks like there was some overfitting. Okay, so now let's do the same network. You can see that it's the same architecture, exactly the same, but we're not gonna replace the weights of the embedding layer this time and see what happens. So before we didn't train the embedding layer, but now it's gonna be trained. So we're not gonna get the weights from the Stanford predetermined embedding, and let's compare how good this network is gonna predict the evaluation of movies compared with the, and you can see that the validation accuracy is the accuracy is 96% because it's overfitting, but 70, this is the one that matters, the validation one, 70%. Without getting into the hassle of loading this data from Stanford and putting into a weight layer, we went to we had the same, a little bit better actually. Yeah, although it took maybe a little bit more time to train because one more layer to train, but it wasn't that much really. Okay, so yeah, as you can see again that still we're overfitting. Okay, so now we're gonna evaluate how well we train the network. So we're gonna use the test data again. For some reason, the data that the raw data from the IMDb database didn't have a training folder, so I'm using the test data. So I'm basically doing the same pre-processing similar to what we did before, and using the loading the weights of the model and evaluating them and see the precision. The precision is going to be higher than the book says because we're going to using the same folder, but at least you saw how these networks are trained, how the embedding layer can be trained or be predetermined, and now we're ready to see how recurrent neural networks work for natural language processing and also LSTM. That's going to be the topics in following videos. Thank you for watching. Bye.